So, for that reason, Major, you're fired.
So, Major, how do you feel about being fired?
I feel okay about being sacked, really, you know. Easy come, easy go. With a talent like mine, there'll be plenty of opportunities waiting for me round the corner, honestly. One day, Benito will look back at this day and think, what a terrible mistake. But you know what? I'm gonna stay positive, you know. You know what? I don't know. I don't need him anymore, you know. As Little Mix would say, shout out to my ex. You're really quite the man. Something like that, yeah. Anyway, I'll see ya. Nothing but happiness for me. Honestly, mate. See ya.
Hello, Major Thompson. We're just heading out.
You bet I am, mate. Have you got a clue what you've just done? You've made me lose my job. 4 years in this business, you know what I'm saying? And you come with a pair of scissors like this, and that's all you can do. And you get me sacked.
It's okay.
No, don't keep telling me it's alright. You know bloody shit. Off you go. Bloody hell. Hang on, I might have left some in here. Sorry. Right, hello everyone, it's the 11th video in the Sensory Ecology series, and today we're going to be talking about underwater vision and the challenges that animals face if they want to see underwater. But before we look into the actual animals, as usual, we have to look into a bit of physics. We need to look at the actual physical challenges these animals must face, and then we can go into something interesting. Okay, so there are several quantities that we need to take into account when looking at underwater systems. The first is irradiance, okay, and not to be confused with radiance that we're going to be talking about later. Irradiance, these are the units. It's measured in photons per second per meter squared. We mentioned it in the first ever video on vision. So it basically measures the photon flux here, and to measure it you need a detector which receives light from all directions. And as you might expect, as you go deeper in, say, the ocean, the irradiance decreases. In fact, it's been given an equation, and this is the rate at which it decreases. It's a classic exponential equation. There's loads of e's there, but the small e signifies that it's an exponential decay equation, because e is the exponential function. But anyway, we don't need to worry about that. Got a bit too mathsy now. Now, from irradiance, we can work out transmission. We talked all about that in the 7th video. This can be done for oceans and inshore waters as well. Now, the transmission in the oceans is nearly always greater than in inshore waters, and we'll talk about that, why that is in a second. But another guy called Gerlov, he was an oceanographer, decided, I know what could be a fun thing to do. Let's classify all the different types of water there are in terms of their transmission. Yeah? Great activity to do on a Sunday afternoon, I think. So he devised what we call the Gerlov water types, and those all relate to how transmissible light is through them. Okay, where in inshore waters, type 9 is like really murky water, hardly any light gets through that, and type 1 is quite clear. Oceans, there aren't quite as many. There's type I, there's type IA, type IB, type II, and type III, right? Where the transmission value is lowest in type III, okay? Let's have a look at a graph of this just to show you what I'm on about. So what we see here is that eutrophic water has the lowest transmission value. Now, eutrophic water is where lots of primary production is happening, lots of photosynthesis. This is water with loads of algae on the surface that are absorbing all that sunlight for use in photosynthesis. And because of that, no light can get further down from the surface, so the transmission decreases quite rapidly, and of course the irradiance does as well. The spectral composition of that light differs between inshore and ocean waters as well. In inshore waters, the peak wavelength of transmission is a bit higher than that in oceans. So if you look at that graph then, type I, type IA and type IB are definitely the clearest waters. They have the highest transmission values, right? And that's because these type of waters tend to be what we call oligotrophic. There's not many nutrients there at all. And if there's not many nutrients there, that means less stuff can live there. So that means there's less algae, which are going to be absorbing all that light, photosynthesis. These Gerlov water types can be plotted across the world's oceans and then confirmed using satellite images. And we can see that with the oceans, those areas which are type 3, type 2 kind of areas, the areas where there's low transmission, are areas of large upwelling sites. Now, where there's lots of upwelling in the oceans, that means there's lots of productivity. Nutrients are being brought to the surface, which allows algae to thrive, and they form the real basis of the ocean food chain. Okay, so without them, there wouldn't be anything else. Okay. And it also seems to be very closely related with chlorophyll, obviously, because that's what the algae are using to photosynthesize in the first place. So this is like off the coast of Peru and West Africa as well. They're the real rich areas of high productivity. And as I said before, with depth, many of the wavelengths just simply disappear. They're absorbed by the oceans, so don't get transmitted. About 1,500 meters, the only wavelengths that's reached down there is the blue wavelengths. Yeah, that's why the sea's blue, because blue transmits much better in water. Okay, or in ocean water anyway. This creates what we call a homochromatic environment. Yeah, which stands to reason, I suppose. And our limit to sensitivity of downwelling light, if we were to, if I was to take you and plunge you down deep into the oceans, you wouldn't be able to see anything at about 900 meters. I mean, your eyes would probably popped out your head by then, but theoretically speaking, that's where you'd stop seeing stuff. Variations in this colour will obviously due to the absorption of water, but then other organic compounds as well. So chlorophyll, as mentioned earlier, will have an effect on the colour of the sea. And also DOM. What's DOM? DOM stands for dissolved organic matter. So that means basically any other organic material that's floating around in the ocean. Okay, another thing which you can measure is radiance. Now, it sounds a lot like irradiance, and the units are very much like irradiance. So, irradiance was photons per second per meter squared. Radiance is photons per second per meter squared per steradian. Now, what's a steradian? Now, if you did A-level maths, you'll know that a radian is another way of measuring an angle, instead of degrees. Very common in trigonometry. A steradian is the 3D equivalent of that. Okay, so it's basically a way of measuring an angle in 3D. And the smaller the angle, the better, really. Here, to measure it, a light detector will only allow light to hit it from a certain direction. So, irradiance tells you the photon flux, but radiance tells you the direction in which that light was coming from. And this can be measured using something called a Gershon tube. How very fancy is that? So, that's a bit of background. Now, when light hits water, naturally, refraction's going to happen, the bending of light. And it's this bending of light which creates what we call Snell's window. What's Snell's window? Well, imagine you're a fish in the sea and you're looking up, right? You look up to the surface of the water. Well, the area in which you can see out of is what we call Snell's window. There'll become an area where all you see is just a reflection of yourself. Okay? And the angle of this Snell's window is always 97 degrees. And that's all to do with the physical properties of the refraction of light. So any light arriving from greater than 97 degrees will be reflected. Okay, so you'll see a mirror image. Okay, so if you're a fisherman and you want to get a fish, you want it to be out of Snell's window because that way the fish will not be able to see you. Now in the oceans, there's a lot of wave action, isn't there? And that creates a lot of variability in the intensity of light in the oceans. So if you think about it, as those waves are moving along the ocean, they create temporary lenses, if you like. So let's see a wave that goes like that. That will create a lens focusing light at a particular point. But then it will move away and focus light at another point. So that creates all these interesting ripples and patterns on the sea floor, as you've probably seen. This causes variability in the intensity of the radiation arriving at the sea floor, and of course that's going to affect the animals that live there. Once light's in the water column, three things can happen basically. Light can either be absorbed, by molecules, it can be transmitted, like the blue wavelengths, or it can be scattered. It can just jump around the place, bumping into molecules as it goes down, okay? And it's that which creates what we call the veil of light, and it's very useful in the camouflage of many species, and that is what we're going to be talking about now. Now it's pretty obvious that when you're close to the surface, there's not that much scattering compared to deeper down, because deeper down, well, light's got more molecules to get through, so there'll be way more scattering. So light coming in from Snell's window is going to be far greater than any upwelling light which has been deflected upwards because it's bounced off a water molecule or something. But as you get deeper, the ratio of light coming from above and below starts to get a bit more symmetrical, at the vertical axis anyway, and there comes a point where the distribution of light becomes what we call asymptotic. It doesn't change, okay, so that's at really deep depths. The exact depth of that depends on the water body, it depends on the Gerlov water type. Okay, now animals can use that to their advantage for special different types of camouflage, but before we do that, let's just get some terminology sorted, okay? You can divide the ocean into four main parts, okay? The first 200 meters of the ocean is what we call the Epi Pelagic Layer, right? Below that, about 200 to 1,000 meters, we call that the Mesopelagic. There's still some light there, it's also called the twilight zone, but obviously nowhere near as much light as there is in the Epipelagic. Most life in the oceans occurs on the surface, the Epipelagic, or the eutrophic layer, if you want to be more specific. Below the Mesopelagic, we have the Bathypelagic. That's 1,000 to 4,000 meters deep, so pretty deep now, okay? And that's where all the deep sea living creatures live. Very spooky, we'll go on to that. And then below that, 4,000 and below, that's what we call the Abyssopelagic, but barely anything lives there, quite frankly, so we don't need to worry about the Abyssopelagic. So the type of camouflage that an animal uses depends at what depth it's at, in which of those four regions of the ocean they're in. Now in the upper Mesopelagic, there's still quite a lot of light there. So that means animals can use that to their advantage. There are many animals which are transparent. Okay, so a predator could just see through them and not know that they're there. But that is quite difficult to achieve really, especially when it comes to photopigments in the eye. The eye, those pigments that we've been talking about for ages, have to have a particular refractive index, and that refractive index has to be different to the rest of the body of the animal. So there's no way an animal can become completely invisible because it needs to see somehow, okay? So it's actually quite difficult to be transparent. If you can, that's great because it reduces the contrast between the body and the background. So still quite a few animals use it even though it's not perfect. Another example of camouflage is mirror camouflage. So just reflecting the light that comes at you. That can confuse a predator. Because remember, as you go down, there's a lot of side scattered light. Okay, so light which has been scattered horizontally will hit you and your body can just reflect it right back at them. So again, it reduces the contrast. Now as you go lower and lower in the Mesopelagic, animals start to become red. Why is that? Well, we talked about earlier how the spectral range, the wavelengths that go down with depth, the range of those wavelengths gets narrower and narrower as you go deeper and deeper, to a point where you can only see blue. Okay? Red attenuates quite quickly with depth in the ocean, so there comes a point where you just simply can't see red. That means that anything red in the lower mesopelagic will be perceived as black. And because there's not that much light down there at the lower mesopelagic, there isn't that much side scattering going on. So all you can do is just match the background, which is black, which is a pretty good idea. Right, okay, well you know what they say, right? There's plenty of fish in the sea, that's what everyone says. So let's talk about fish then. And in particular, fish vision. How do they see? Well, a goldfish, for example, is pretty good at it. It's got 5 different opsins. Obviously, it's got its RH1, that's its light-sensitive opsin, and then 4 others. That makes them a tetrachromat. And they're sensitive to a broad range of wavelength. They can see from the far red, which is just going into the infrared, all the way up to the UV. So they're pretty good. Now, if you were to look at the lambda maxes, we talk about lambda maxes a lot, of teleost fish, so teleosts are basically every fish you can name, basically, apart from a few obvious examples. If you were to look at teleosts and look at the lambda maxes of their opsins, and then compared them between the different habitats that they lived in, so in this study they looked at differences between coastal marine and freshwater teleosts, then the lambda maxes appear to be quite distinct. So that means those opsins are perfectly tuned in to the light environment that they're in, so they can see as good as they can possibly see given the environment. For example, long wave rods are only found in freshwater teleost species. And because the teleosts are so diverse, this might have evolved multiple times. Okay? But here's the situation then. Not all fish are just, right, I'm a sea fish, I'm a freshwater fish. There's lots of migrations happening. Some fish have to live in both environments. So how on earth do they cope? Some terminology here, catadromous fish are fish which go from freshwater to the sea to breed. Okay? And that's what fish like eels do. Eels, absolutely fascinating fish. Probably one of my favourite fish, if I'm being honest. So eels, the European eel, has a fantastic life cycle. It spends most of its time in freshwater rivers and lakes in the UK, and then moves off, all the way off to the Sargasso Sea to breed. Okay, so 2 very different environments, 2 very different Gerlov water types. So how does it adapt to that? Well, eels are pretty incredible, really. They are able to convert their chromophore from rhodopsin into porphyropsin. Okay? And that porphyropsin is perfectly adapted to a more freshwater lifestyle. The difference between these 2 molecules is only 1 double bond, so it's quite easy, but it means that porphyropsin has a completely different spectral sensitivity, which is suited to its particular environment. Amazing. Not only that, eels can also change gene expression in the protein component of the opsin. Well, the opsin is the protein component. And a similar sort of thing is seen in the rudd, which is another British fish species, but this only swaps the chromophore. It doesn't do anything to the opsin. Okay, there's no changes in gene expression there. Pollock, which is a fish which you can eat, I think. I don't think I've ever had pollock, but I don't know about pollock. God, I think people have talked a load of pollock, if I'm honest. But they have 2 SWS genes, okay, and they'll change the relative expression of those genes depending on the stage of the life cycle or the environment in which they're in. They can also change this with differences in prey abundance, so pretty nifty stuff this is. Okay, that's for normal fish. What about deep sea fish, those that live in the bathy pelagic where there's barely any light at all? How do they see? Now obviously in the deep sea there's a close relationship between the light that's available and the lambda max which those opsin genes are tuned into. naturally, right? So as we talked about, I mean, there isn't a lot of light in the Bathy Pelagic naturally, but as you go down, there's more of the shorter wavelength, so the blue kind of light. Yeah, so that means the lambda max of those opsins will be nearer those wavelengths. Now sometimes the spectral sensitivity of opsins doesn't quite match the light that's available, just a little bit wrong. But here, the only example of a spectral sensitivity being exactly right, like bang on the money to the type of light environment, that's seen in the deep sea. Okay, so that just shows how strong the selective pressure has been on these opsins to move their lambda max so it's at just the right value. Now I say perfect, but at a glance it may not seem to be the case. The lambda max of these opsins is around 480 nanometers, right? But the peak wavelength at that kind of depth is around 450 nanometers. So there's a bit of a mismatch. So how on earth do you explain that? Well, the answer lies in bioluminescence. Okay, bioluminescence, the biological production of light. Very useful in the Bathy Pelagic when there isn't much light around, right? And obviously it's in the terrestrial environment as well, but we don't need to worry about that. It's basically the same thing. It's a reaction between two chemicals, luciferin and an enzyme called luciferase, okay? That's quite easy to remember, isn't it? And the peak wavelengths in the Bathy Pelagic that this bioluminescence is at is around 470 nanometers, so within the range that we've been talking about. There's great diversity in how bioluminescence can be used. It can be used to display, to track mates, it can be as a warning to potential predators, it can be used to attract prey, it can be used to mimic other animals, a whole host of different things, okay? The list is endless, it's very adaptable indeed. Now, if you look into the eyes of these deep sea fish, I mean, there isn't a lot of side scattered light, so it makes sense actually to look upwards instead. Because there is more light. You may be able to detect the silhouette of a big, I don't know, shark or something up ahead, which could get you. So that's why loads of fish have eyes looking upwards in the deep sea. This results in some really weird looking eyes. Some have tubular eyes, such as the fish Dolichopteryx. Let's have a look at that. Pretty strange. Now these eyes, in comparison to the body, have quite big lenses. That means they have what's called a low F number. That's the ratio of the focal length of a lens and its aperture. Okay. Now that's all very good to detect downwelling light, because it means more light can enter if you've got a bigger lens, okay? So it increases sensitivity. But it restricts the field of view of that fish, because you can only look in a certain direction if you've got tube eyes. Now the hatchet fish is a pretty interesting example. It has what we call ventral camouflage. Along the ventral side of its body, it has these photophores. Now photophores are the cells which emit light. Okay, so that's where all the bioluminescence is coming from. And it emits light which matches the downwelling light coming down. And this light is matched in the spatial and the spectral distribution, so it basically becomes invisible if you're a predator who's looking up, you know, with the downwelling light coming in, you can't see it. It also helps that this fish is extremely thin as well, so it's got its life pretty much sorted. Bioluminescence, of course, can also be used in prey illumination. The classic example is the anglerfish, of course, with its big hook, which has a bulb, if you like, at the end of it, which allows it to look for prey. Now, the animals have a bit of a problem here, because the easiest types of wavelengths to produce in bioluminescence is a kind of bluey colour. As we saw here, the peak wavelength is around 470 nanometers. Okay, but, well, there's two problems really. First problem is, well, everything's blue anyway, okay, and the spectral sensitivities of the eyes of the fish in the Bathy Pelagic in the deep sea are tuned into blue wavelengths. So if you want to sneak up on your prey with a blue torch, then they're going to spot you a mile off. So it's actually probably better to use red bioluminescence, even if that is much more difficult. Not to worry though, in nature, of course, there's some fish that have mastered this, and these are two general that I have. I'm going to pronounce this terribly. Aristostomias and Pachystomias. And these fish can see the red because they've got opsins, which was especially adapted for those red wavelengths, okay? Now, admittedly, they occur over a short range, and the fish has got to be pretty close to the prey for it to detect it. But it still works pretty well. So this just looks like an evolutionary arms race waiting to happen, doesn't it? These fish can see the red bodies of their prey, but the prey can't see them. Amazing. They've got it sorted, haven't they? Because remember, most animals in the deep sea are sort of black and red anyway. Okay, so perfect, right? Now, there's a fish that really is a champion amongst all of them, I guess, and that is the black dragonfish. Have you heard of the black dragonfish? Well, you do now. So here's a picture of one. The Latin name is Malacosteus niger. Now these guys have really taken it one step further. They have a post-orbital photophore and a sub-orbital photophore. Now the post-orbital photophore emits blue light and the sub-orbital photophore emits far red light. Okay, so two quite different wavelengths here. Okay, so they've got it sorted. But then how do they see this? Well, the way they see this is pretty incredible, okay? So they've got an opsin which is tuned in to the blue wavelength. It's not exactly right, but near enough, okay? Now, the opsin that's tuned into the far red isn't very well aligned at all, right, with the wavelength. So the lambda max of the opsin is quite different to the wavelength that they're emitting. Okay. Now obviously this light could be used in a private communication system between conspecifics, but also it can be used for prey detection as well. Now, the way the black dragonfish gets round this is by having what's called an accessory pigment. And the peak sensitivity of the accessory pigment is around 678 nanometers, okay? So that moves that absorbance curve more towards where it wants to go, okay? Which is the light that it emits using its photophores, okay? Now, where does this accessory pigment come from? Well, if you look at the molecular structure of this pigment, you'll see that it looks very similar to a molecule called chlorophyll. Now, chlorophyll, as the name suggests, is found in bacteria, and it's very similar to the accessory pigment, except that it doesn't have magnesium. The accessory pigment doesn't. Okay, so what the scientists think is happening here is that these black dragonfish are feeding on copepods, so small little crustaceans, and it's those copepods that feed on the bacteria, which has this chlorophyll. So these fish are obtaining this accessory pigment from their diet, indirectly as well, because they're eating the copepods and the copepods have eaten the bacteria. Okay, so after they've taken it up, then they can modify it so it's perfect. The accessory pigment's perfectly there. So there you go. Forget about eating carrots to improve your spectral sensitivity. This is a lot more important, because otherwise, if they didn't eat these copepods, then they wouldn't be able to see where they were going, quite frankly. So that's a lovely little example for you, and that's all I've got time for. Next time we'll be looking into a particular interesting area of visual ecology, and that's polarization vision. I'll see you next time.